Alright, so in this video we're going to keep talking about energy, and so the one we're going to focus on now is going to be potential energy. And again, we're going to kind of use a little bit of that middle school, physical science definition about potential energy being stored energy. Okay, and so the way potential energy really comes about is that any conservative force, so any force that conserves quantities in physics, has a potential energy associated with it. In Physics 1, the two big potential energies that we're going to speak about are going to be gravitational potential energy, which we're going to abbreviate or give the variable U sub g, and then it's going to be, the other one's going to be elastic, right, or spring potential energy, which we give the variable of U sub s. Okay, there's any force that's conservative would have a potential energy associated with it. All right, and so gravitational potential energy is the amount of work, right, required to move it, and it says it, right, it should be an object, right? I guess this came from somewhere else and I copy and pasted it probably. So it's the amount of work required to move an object from one location to another. And so one thing that you're going to notice, that potential energy is going to be based on locations, right, or positions. All of our potential energies are based on position. And so the formula for gravitational potential energy is just simply mgh. The way to think about gravitational potential energy is it's the work that you do against gravity. Okay, so we did the pumpkin question when we in the work video, right? We're actually giving that pumpkin potential energy because we were moving it from a position of 0 meters to a position of 0.80 meters. So we are doing that much work against gravity. Again, so since this is energy, right, the unit would be joules. Here just and right now, right, these are gonna the example problems are gonna be this simple, right? And so you have first question: find the gravitational potential energy of a 65 kilogram person sitting on a diving board that is 3 meters high. I mean, that's very straightforward. You're just going to multiply the three values. So U sub g equals mgh. So 65 times 10 times 3, and you get a potential energy of 1,950 joules. Right? So that's very straightforward. The next question, talking about a candy bar called the Mountain Bar, has a nutritional energy content of 8.87 times 10 to the 5th joules. When we eat food, right, the amount of joules that we intake is the amount of calories that we eat. And so really 1 calorie is 1,000 lowercase calories. Okay, in fact, the capital C calories, our food calories, are actually kilocalories. And so if you in chemistry you did probably stuff like calorimetry, that's where it comes from. And the word itself comes from that when they were studying or when they were proposing ideas about heat transfer, that there was a fluid called caloric, right, that was exchanged between the two objects. And so that's kind of your base for the word calories. So there's your physics history lesson for the day. And so this question is saying, okay, how high can this mountain climber, how high can they climb if they eat 1 candy bar? And they have a mass of 81 kilograms. So we start with our basic equation, U sub g equals mgh. And so we're going to solve this. It auto-corrected to an arrow, which is weird. So we're going to solve this for h, and so it's going to be simply ug over mg. And so we're gaining 8.87 times 10 to the 5th joules, right? And essentially we have to lift our weight. And so you could see, like, that's how this, so we're going to do 8.87 times 10 to the 5th joules of energy is what we're gaining. And we're going to essentially lose it by lifting our weight, right? This 81 times 10. So we're going to do 8.87 times 10 to the 5th divided by 810, because that's what 81 times 10 is. And so you're going to be able to climb 1,900 or 1,095 meters. Okay, and then sometimes, if they want this in a more, a non-science world, right? So they may ask you to report your answer in miles, just to give you a comparison. So 1 mile is 1,609 meters. And so we would take that 1095 and divide by 1609, and we find that that's the equivalent of 0.68 miles. So less than 3/4 of a mile this climber will be able to climb by eating one candy bar. I mean, they could throw all kinds of questions at you with this and say, how many candy bars will they need to eat to climb Mount Everest or something like that, right? And so you just have to know how high they have to climb, how much energy they would need to use, and then you can do a simple conversion, right? One candy bar is 8.87 times 10 to the fifth joules, and so forth. Okay. Now, the other potential energy that we do talk about in AP Physics 1 is spring or elastic potential energy, and that has to do with elastic materials. So materials such as springs, rubber bands, they're elastic because they're going to return to their original size and shape after being distorted or deformed. Okay, so the potential energy stored in an elastic material, right, is called elastic or spring potential energy, which is abbreviated U sub S. We talked about that, when we're just kind of loosely defining them. So when a spring with a force constant K is stretched or compressed by a distance x, the amount of work done on the spring is W equals 1/2 kx squared. If you take AP Physics C, or if you take calculus-based physics, you would actually derive that. You would get that equation through the use of integrals. And this work is really stored as that EPE, that elastic potential energy. Okay, and so this equation is also equal to the spring potential energy. So what happens, here are a couple examples. So a spring with a spring constant of 120 newtons per meters is compressed a distance of 2.3 centimeters. How much spring potential energy is stored in this spring? So this is just a straightforward equation, right? And so here's where they try to mess you up a little bit, is they give you the compression distance in centimeters, but you need to make sure that this is converted to meters. And so we're going to make sure you do that. And the other reason why you need to see this is because your K value is given to you in meters as well. And so you would do 1/2 times 120 times 0.023 squared. And what you're going to see, a spring with like this doesn't have a lot of energy stored in it, because it doesn't take that much to stretch it a meter. And so this is, I forgot to square it. Common mistake is not squaring. So you're going to see there's going to be 0.03174 joules of energy stored in this spring. So if this number goes up, if your K value goes up, the amount of energy stored is going to go up as well. Garage door springs generally have a K value of roughly 10,000 or higher. So if I were to plug that in, even moving it 2.3 centimeters, I mean, there's going to be a lot of energy stored in that. The next question talks about hockey sticks. I had to put this question on here because, growing up I played hockey. And so if you watch NHL games or college hockey, you see that the sticks do bend quite a bit. And so a hockey stick stores 4.2 joules of potential energy when it is bent 3.1 centimeters. Again, this needs to be converted to meters. Now, if we treat the hockey stick as a spring, what is its spring constant? And so here is our equation, and we're going to solve this for K. So you're going to end up with 2us over x squared. And so now you just plug in your numbers. So 2 times 4.2 over 0.031 squared. Now, just as a note, Mr. Londa does not use, when he plays hockey, does not use a stick that likes to bend a lot. That's not the game I play. The game I play is in front of the net. So all my shots need to be short and quick, so I don't necessarily have a lot of bend to my stick. Now, I've played with guys who had a lot of bends to their stick, and they may have had harder shots than mine, but again, that's not the game that Mr. Londa plays. Mr. Londa plays in front of the net, usually getting beat up a lot by the defenseman and so forth. And so this stick would have a K value of 8,741 newtons per meter. So what does that actually mean, right, this K value? So what that means is it takes 8,741 newtons to stretch the spring 1 meter. So if we had a hockey stick and we attached it to the table, I would have to put 874 kilograms, right, to watch that stick bend, right? So if this is my stick, right, I would have to put 874 kilograms here to watch this thing bend 1 meter. Okay, so 874 kilograms, if you want to talk about in terms of pounds, is approximately a ton. Right, 2,000 pounds. It's 1,932 pounds. Right, that's a lot to get the hockey stick to bend. Right, but these guys generate that much energy when they take shots, and some bend further. Right, but they also may have looser K values, right, or smaller K values. So potential energies, that's what we talked about in this video. Now we're going to start focusing our efforts into combining all of our energies into one big concept, working our way all the way up to conservation of energy.